Hello physicists, welcome to our March 29th edition of physics. Overall, people did very well on the quiz this week. The only question that there was much trouble on was this one, where you had the skater pushing herself off of a wall, pushing herself backwards, and it asks for the magnitude and direction of the impulse on the skater. Most people got this right. I believe what was going on with this one is probably that people were calculating the force instead of the impulse. So impulse, of course, is force times time. They give you the number of seconds, but you don't actually need to calculate that. You just need to use the kilograms times minus 1.2 meters per second. And the impulse of the wall on the skater is such that it pushes her backwards. Of course, she pushes the wall forwards as well. So I'm not too concerned about this because I feel like people mostly got the right idea on this one. So this was our delta P, which was our minus 1.2 meters per second times 28 kilograms. Remember, momentum is mass times velocity. So that's the final velocity, and then minus 0 because her initial momentum is 0 if she's not moving. Okay, but other than that, the quiz was pretty good. Now, let's talk a little bit about where we're going in the next few weeks. This week is a little bit of a weird one because of Easter break. We have this coming Friday and the next Monday, so Good Friday and Easter Monday we have off of class. I also want to make this week Wednesday remote. And partially that's because I think people are going to want to go home. And partially it is because I have a daughter in preschool and she has an Easter program. So I don't want to miss it. So anyway, but I will be posting a video on Wednesday, and there will be new material. So please really make a point to watch it because it will be covering stuff that's new, not just reviewing over old stuff. Now, the next homework is a monster, and it's over chapters 10, 11, and 13. We're skipping chapter 12, not because it's not important, but just because we don't have time. And that is not due for quite a while. It's not due till April 12th. However, again, I know we've had one of these monster homeworks already, but this one, again, I want to emphasize that if you try to leave it till the end, you're going to be in hot water. So please, every time you have a class period, try to get about 6 or 7 of the problems done, and then you'll be fine. If you leave it all to the end, it's going to be bad. And so the homework is due April 12th. We're going to review on April 12th and April 14th. And then the tests 3 we're going to try to have on April 16th. And it's over a bunch of stuff. It's over chapter 9, which is momentum, chapter 10 and 11, which is rotational dynamics, and then chapter 13, which is going to be gravity. And then after that, we are almost done with our semester. We're going to do a little bit about heat and temperature, and then get ready for our cumulative exam. Okay, this is what the monster homework looks like. So please find that on Canvas. I know you have a homework that was due. I'm not making you hand it in till Wednesday. I have a place on Canvas to hand it in. I know if we're having our class remotely, that's a good place to hand it in. If you want to hand in a paper copy, you can always leave that by my office in the bottom floor of Mickle. Okay, so what did we do last week? Last week we talked about rotational coordinates and kinematics under constant acceleration. So we talked about these kinds of coordinates for which the entire disk is supposed to have the same motion. So our example that I talked about on Friday was this one where the outside of the disk is moving in real life, in real space. It's moving more quickly on the outside than on the inside, but it's convenient to talk about coordinates in which these two are moving the same. And so to go from your angular coordinates, angular position, angular velocity, angular acceleration, to linear, you can just multiply by r in each case. And we talked some about constant acceleration, at the constant angular acceleration model, which is basically just the constant linear acceleration model, except we're kind of doing it as a substitution cipher, where every time you had a v, we put in an omega. Every time you had an x, we put in a theta. Every time you had an a, we put in a alpha. And so these equations look quite different, but they're all saying exactly the same thing. Now, the thing that was new on Friday was that we added a direction, a vector direction for our angular velocity. And the way that we did it was we said you've got a direction of rotation. Your thumb is, if you use your right hand and spin it around in the direction of the rotation, your thumb should be pointing in the direction of the angular velocity. We're going to try to sharpen that up a little bit in today's lesson. And the other thing we talked about a little bit on Friday was that if you have the rotational inertia, which I sometimes call the moment of inertia just because that's how I learned it. If you go and you take a second course in this sort of thing, there are many moments of inertia. You can have a second, third, whatever. But let's not get into that in this course. So we talked about the rotational inertia and how the kinetic energy is related to the rotational inertia, where it looks like sort of a rotational mass, where instead of having 1/2 mv squared, you have 1/2 I omega squared. Okay, so what are we going to do today? Well, we're going to do quite a bit. First, we're going to talk about how are we going to generalize this idea of rotational inertia. How can we do it for any old body that we want? And it turns out we're going to do it by breaking up our mass into little tiny masses, differential masses, and taking the integral. Then, what we want to think about, we're thinking about, let's suppose you have this object like this. How do I get it to start spinning? Well, you have to apply a force. Okay, well, let's say that this is on an axis of some sort. Will any old force do? No. For instance, if I apply my force radially, it doesn't start my disk spinning at all. So we developed the idea of torque as the part of the force that's acting at a distance out and that acts perpendicular to the direction of the angular velocity or angular acceleration vector. Okay, so this is all a little bit confusing, but we'll go through it and it'll make sense by the end of today. Then we're going to use that to rewrite Newton's second law in rotational coordinates. So we had F equals ma, and we'll end up with torque equals I times alpha. So torque is like angular force, rotational inertia is like angular mass, and angular acceleration is, I guess, like angular acceleration. Okay, and then finally, to get ourselves someplace where we can do something new with this, we're going to introduce the work energy theorem in rotational coordinates. So just as we had work is force times distance, in this context, work is going to be torque times angular displacement. And just as we had that the amount of work that we had done on a linear object was the difference in its final and initial kinetic energies, that's the same. And also the power is the force times speed. That's also the same, except it looks a little bit different because it's torque times angular speed, angular velocity. Okay, so let's go slowly through this and make sure that we understand each one of these points, because they're all related, but they're all a little bit subtle. Okay, so how do we find out what the moment of inertia of an object is? Well, it's a little tricky because if you see this definition, it depends on how far is the mass away from the rotational axis. So if I have an object like a pen and I'm spinning it around the middle, it's going to have a different rotational inertia than if I'm spinning it around the tip. Okay, in fact, if I spin it around the middle, more of the mass is going to be close to the center, so its rotational inertia is going to be smaller. The closer your objects are to the axis of rotation, the smaller your moment of inertia is going to be. So to make this exact, let's show how to do this example for two different orientations of a thin rod. Now, a thin rod has its mass spread uniformly along the rod. So if we wanted to say, what does that dm look like? It looks like the linear mass density of the rod, which would just be the total mass divided by the length times dx. Okay, so I have a differential mass, which is the linear density times the differential length. Now, once I have that, I can make a calculation. So, for instance, in this case, this is going to be x equals minus L over 2 to x equals L over 2, where x equals 0 is the where my rotational axis is. Okay, so if I now just plug into my formula, what I will find is that I equals minus L over 2 to L over 2. And now I'm going to have r squared, that's distance, so that in this case it's just going to be x squared, m over L dx. Okay, so here I can do this integral pretty easily. That's going to be 1/3. So I'm going to take my m over L out front, m over L times 1/3 x cubed. And then this is going to be from minus L over 2 to L over 2. Okay, so I is going to be 1/3 m over L times 1/3 L over 2 cubed minus 1/3 minus L over 2 cubed, which equals 1/12 mL squared. Okay, so that's one way. The other way, I'm going to have the same difference, but the only difference is that my rotation is going to be about this end of the rod. So my x equals 0 right there. That's where I'm rotating around. And then my x equals L is over here. And so if I want to calculate my rotational inertia, it would be 0 to L x squared m over L. This is, look, this is all the same. And my I would then be m over L 1/3 x cubed from 0 to L. And look, here I'm done immediately because this is just going to be 0. Okay, so 1/3 m L squared. That L on the bottom cancels out one of the L's in the L cubed right there. Okay, now you might be thinking to yourself, oh my God, this seems terrible. How am I going to do this? Well, the good thing is that most of the time I'm going to give you those. All right, so don't freak out. I'm going to give you a bunch of these. Some of these you should be able to calculate. Others of them would be hard. For instance, like this one, a solid cylinder about a central diameter. That one I would have to think about for a while. I think I could do it, but it would take a little thinking. All right, so here's the question I have for you to think about. Which one of these geometries, the hoop or the solid cylinder, would take less work to get spinning? So I'm trying to have you imagine a situation in which you have the same amount of mass. Maybe these are made out of bread, so you can squish up the mass at will. And you had the same amount of mass in a hoop or a mass in a disc. Now, which one would have the bigger index or the bigger rotational inertia? It turns out it would be this one. Why is that? Well, the rotational inertia tells us about how the mass is distributed within my object. So in this object, the mass is farther away on average than it is in this object. In this one, you have a lot of the masses right around the axis of rotation. Okay, so that's why this one is half. The rotational inertia is 1/2 of that of this, and in fact, this has very clear sorts of experimental outcomes. What I showed in class today, I took this hoop and I took this disc, and I rolled them both down a ramp. Now, it might not be obvious to you right now which one of these would get down first. This one's a bit heavier. This one's a bit lighter, but heavier objects, of course, have more inertia. It takes more force to get them moving. As it turns out, this one makes it to the bottom of the ramp before this one. And the reason is, relative to its mass, it has the smaller, if you take the moment of inertia divided by the mass, this one gives you a smaller number because more of its mass is towards the center. This one, all of the mass is around the edge. Okay, so as I said, I will give you these. Of course, if you enjoy doing integrals, I encourage you to try these because they're cute and not too bad to do. Okay, here's the type of rotational or moment of inertia or rotational inertia problem that you will need to know how to do. So it says rank the 3 spheres according to their moment of inertia. Okay, so the idea is we're taking these and we're kind of spinning them around on a stick. All right, so this first one, what would our rotational inertia be? It would be m, so it would be 36 kilograms, r squared times 1 meter squared. So for that one, my I, so let's label them A, B, C. A, the rotational inertia is going to be just 36 kilograms times meters squared. Notice this does not have the units of mass. It has the units of kilograms meters squared. The reason for that is because our angular units essentially don't have meters in them, so we have to put in extra meters in somewhere. Okay, so B, what's our rotational inertia? I equals 9 kilograms times 2 meters, there's the 2 there, squared. So that's 4 times 9 equals, wait a minute, 36 kilo, okay, let me check again. What about this one? It would be 4 kilograms times 3 meters squared. Okay, so, sorry, this should be 3 meters squared. So this is 9 times 4. What do you know? 36 kilograms meters squared. Oh my gosh, they've really set this problem up well. We have 36 kilograms meters squared on each one of them. Okay, so what's the lesson here? The lesson here is you get the same moment of inertia if you have a little bit of mass far out as you have with a much larger mass farther in. Okay? If you're trying to get this spinning, it's going to take more work to get that spinning than it will be to get this. Why? Because your mv squared, or your 1/2 mv squared, your v is going to be less the closer you are to the middle of the circle. Okay, so it's not tricky, but it can be a challenge to keep all of these definitions straight. Okay, so that's moment of inertia. Now let's move on. We want to accelerate our spinning objects. And the way that we're going to accelerate them is with a torque. And as I said, torque is a little bit like angular force in the sense that it comes from the part of the force that is causing the acceleration. Now this middle one is the picture that I want you to focus on. This is from your book. It says, let's suppose we have this fixed axis of rotation and we want to get this disk spinning around. Well, let's say we apply a force. The only part of that force that is going to matter for getting this to go and start spinning around in a circle like this is the part of the force that's in the radial direction. This part of the force that's in, or sorry, not the radial direction, that's in the tangential direction. The part of the force that's in the radial direction doesn't do anything as long as our rotation axis is pinned down if it's stuck. Our object is only going to be able to be accelerated in that tangential direction. So that's what our sine theta is doing there. Is it's picking out this side, this component of the vector. If you think about it as an x and y component, it's that y component of the vector. And as you see, the torque is bigger the further out on the object that you push it. So you get kind of a mechanical advantage based on this. Now, where we're going to go with that is that torques cause angular accelerations, and I'll show you how that works mathematically in a couple of slides. But what I want you to notice about this is you'll remember that on Friday we talked about how angular velocities have a vector associated with them, and the vector is pointing perpendicular to the direction that the object is spinning, as determined by your right-hand rule. So in this one, I want you to look at that picture. What direction would this cause the rock to spin? Well, if you're saying counterclockwise, you'd be right, and using your right-hand rule, that would be a angular momentum or an angular velocity vector pointing out of the page. Similarly, it would be a torque pointing out of the page. So if you have a torque pointing out of the page, that causes a change in angular velocity in the direction that would be out of the page. And more mathematically, this is what's called a cross product between vectors. And the way that you do this with your right hand is, let's say you have an R, which is the vector pointing toward this point, and then the F, which is the force. You go with your fingers here and go R in the direction of R, and then you curl your fingers around in the direction of F. So in this picture here, R cross F would give you a thumb pointing up. So the torque in this picture is pointing up in the Z plus Z direction. Now the reason this is going to be important is that torques cause angular accelerations. Now let's see how that works. The force in the tangential direction is the mass times the acceleration in the tangential direction. Okay, this is just for a mass that we can imagine being connected to some rotation axis with a massless rod. Now, let's say we want to think about this as being an applied torque. So this force is the part of that force that's being applied in the direction that will cause this to accelerate around the circle. So in the tangential direction. Okay, well the torque would be the force times R, how far out this is. Okay, but this is just an equation, so let's multiply this other side by R2. M-A-T-R. Now remember, if we want to connect up our linear acceleration and our angular acceleration, our AT would be alpha times R. So let's put that in here, and we will have torque equals M alpha R times R. But if I notice what this is just torque, and this is R squared, M R squared. But mr squared for a single point like that, that is the rotational inertia. So I can use this and just say, so this is the I for that particular mass on a rod. And so I would have tau equals I times alpha. Okay, so that's just another way of writing Newton's law for this particular sort of case where you're accelerating around a circle. And just to keep it, just to put a point on this, this is going to be, in this case, a vector, and this is going to be a vector. And this will point out of the page, and that will also point out of the page. So in this case, the tau would be pointing, in physics land, we would write this, like the tip of an arrow, but coming out of the page. Okay, so let's see. Let's do a little bit of practice with this. It says the figure on the right shows an overhead view of a meter stick that can pivot about the dot of the position marked 20 for 20 centimeters. Okay, so this is where we're pivoting around. That is our x equals 0. All 5 forces on the stick are horizontal and have the same magnitude. Rank the forces according to the magnitude of the torque they produce, greatest first. Okay. Now, notice that there are 3 parts of the torque. There's the size of the force, the size of the distance that you are from the rotational center, and the angle between these. So, right here, this has an angle of 0 because R is pointing in this direction and F is pointing in that direction. So the angle is 0. In this case, that torque 5, is 0. Similarly, right here, the force is not 0, but your x is 0. So the R in that case is 0 for this force. It's pushing right at the pivot point, but that pivot point is fixed, so that doesn't cause any acceleration. So your torque 2 is 0. Now, evidently, the way that I'm going to get the biggest torque is by having this as close to a 90-degree angle as possible. Any angle smaller than 90 is not going to give me as much torque. So in this case, my two maximum torques are going to be from F1 and F3. Then F4 is going to be a bit less than F3 was. And then F2 and F5 give me 0 torques. That's exactly the answer that we have here. Now, the thing also to just keep in mind, if you're just looking at this and you think about what's happening, pushing it on your rod from F3 is going to make it spin clockwise. Pushing on F1 is going to make the rod spin counterclockwise. What does that mean? Well, it means that they're going to have torques of different direction. So if you use your right hand rule and practice it, for this one, for F3, you'd have R cross F, R cross F, and you'd have a torque into page. Okay, and then for F1, R would be pointing over in this direction, and then F1 would be pointing like this. You'd have R cross F, torque would be pointing out of the page. Whoops, I got my pen. Okay. I gave you a couple homework problems to practice this. Here's one of them. It says the body in figure 1039 is pivoted at O, so there's your 0, and two forces act on it as shown. If R1 is 1.30 meters, R2 is 2.15 meters, F1 is 4.20 newtons, F2 is 4.90 newtons, angle 1 is 75 degrees, angle 2 is 60 degrees. What is the net torque? Well, torque is force times distance from your axis of rotation times sine of theta. Okay, so you're going to find a torque 1, which is just F1 times R1 times sine of 75. And you're going to have one for the second one, which is 4.90 times 2.15 times sine of 60. All good? And there's a problem. If I want to add up my net torque, it is going to be T1 plus T2. But the trick is that it's actually a vector sum. And so my R1, if you use your right hand rule now, try it out. T1 should be coming out of the page. And T2, again, try your right hand rule. R cross F equals torque should be going into the page. Okay, I took a little break. All right, So when you do the vector, you have to do a vector sum of these two. So it'll be a difference rather than a just straight up adding. Okay, now we're going to try to do something to finish out this video. Remember that when we wanted to change the kinetic energy of a mass, and this was linear, you could apply a force over a distance. That force times distance would be work. And the amount of work that you put into an object is how much its kinetic energy changes. Okay, so 1/2 mv final squared minus 1/2 mv initial squared, this is just in an x direction, equals the amount of work, the force times the distance. And if you take the time derivative of both sides, the amount of work that you're putting in per unit time is the power, that's watts, joules per second. And if you just look at this, this is force times dx. And so if you have dx dt, that would be force times velocity. And so if you're pushing on an object, you can put in energy, make it go faster. The faster the object is going, the more force times distance you have to do per unit time. And so there you go. Now this all transfers over into our angular regime just the same way that we were able to use more or less a substitution cipher and go between all of our x's and thetas, our v's and omegas, and our a's and our alphas. We can also say work instead of just being force times distance. It could be also torque times angular displacement. Okay, and remember this also has units of work. It might surprise you to see that torque actually does already have units of energy because radians, it's a ratio. It doesn't have any real units. But we can use this for a rotational work energy theorem. So if our torque is constant, this would be work just equals torque times the angle that you apply that torque over. And your 1/2 I omega final squared, this is your kinetic energy final minus your kinetic energy initial equals the amount of work that you put in. Now just also like we had, the power is the amount of work put in per unit time. And we had that before was force times velocity. Here, we're going to have it as torque times angular velocity. And we're going to have the same units on that of watts, where watts is a joule per second. So let's just take a quick look at two examples with this. An automobile crankshaft delivers energy from the engine to the axle at a rate of 100 horsepower. Okay, so our P is 100 horsepower, and they helpfully give me the units there. So horsepower, wait, let me see. Okay, so they helpfully give that to me already in watts. So this is equal to 74.6 kilowatts, and I can do that 1 kilowatt to 1,000 watts. Okay, and it says when rotating at a speed of 1800 revs per minute. Okay, so my omega, my angular speed is 1800 revs per minute. 1 rev would be 2 pi radians, and 1 minute would be 60 seconds. So that would give me, canceling out my minutes, canceling out my revs, that would give me my omega in radians per second. Here I have my power, 74.6 times 1,000 would give me my power in watts. It asks what torque in Newton meters does the crankshaft deliver? Well, your P equals your torque times omega. You want to find that. Okay, so the only trick here is making sure that you've got your power and your angular velocity in good units to start. Okay, now my next one is homework with angular energy conservation. This one is a little trickier. Remember what we did with our ideas of work and energy was that we would eventually try to find situations where we would have energy conservation. And what we're going to do in this case is imagine a case where here's your center of mass, and you have now, instead of a pendulum that just has all of the mass at the end, that's how we imagined it at the beginning of this story, now we have a pendulum where the mass is all along the pendulum itself. Now, at this point where the pendulum starts, we can imagine that as being a displacement of our center of mass of that rod. And then when this swings down, so we start out with our gravitational potential energy, and then as this swings down, it gets transferred into kinetic energy. However, this kinetic energy you want to notice is kinetic energy of a rod going around, rotating around a circle around its end. So there's the pivot, and then it goes, and that kinetic energy is once again transferred into potential energy. So let's look here. It says a thin rod of length 0.75 meters. So that's your L. And mass of 0.42 kilograms. Is suspended freely from one end. It is pulled to one side and then allowed to swing like a pendulum, passing through its lowest position with an angular speed of 4.0 radians per second. Okay? So the lowest position is going to have 4.0 radians per second, but that means that, in fact, this whole thing is also going to have 4.0 radians per second. So right there, omega equals 4.0 radians per second. Neglecting friction and air resistance, A, find the rod's kinetic energy at its lowest position. All right, so if you want to find the kinetic energy, it's 1/2 I omega squared. I you can get using that. Omega you can get using this. They just tell it to you. And then B says how far above that position the center of mass rises. Okay, so what this MGH, remember our center of mass was where we were treating this whole rod like a single particle. And so in that case, our MGH is going to come from the kinetic energy that we had originally. So we would have 1/2 I omega squared at the bottom equals MGH of your center of mass. Okay, so you're going to find that. And it's interesting to notice that this actually doesn't depend on the mass. It only depends on the length, because you end up having a mass on this side and that side. And that's the same situation that we had with a point pendulum. Okay, so what are our lessons of today? Rotational inertia quantifies how far mass in a rotating body is spread out from the axis of rotation. In this one, the mass is more spread out from the center. In this one, the mass is more concentrated towards the center. Torque, rotational inertia, and angular acceleration act like force, mass, and linear acceleration in the rotational form of Newton's second law. So that was our F equals ma becomes torque equals I times alpha. And torque applied over an angle does angular work. So here's our work was force times distance, and here our work was torque times angular distance, and increases the body's angular kinetic energy. Okay, and remember our kinetic energy in this case was 1/2 mv squared, and our kinetic energy in this case was 1/2 I omega squared. Okay, so I encourage you after watching this video to go try doing the Chapter 10 homework problems from our new homework set. Please hand in your old homework sets by Wednesday. There's a portal, there's a place open on Canvas, or if you want to leave a paper at my set, at my office. And that's all I have for you today. Good luck, and thank you for watching.